All right, we're ready. So good afternoon, everyone. It is a great pleasure to introduce Dr. Naqvi today. I'll give a brief intro of her bio. She is a research assistant professor in the Department of Nuclear Engineering at Texas A&M University. She works currently in nuclear security and policy, and her research interest focuses on advancing the detection technology that have applications in these fields, such as safeguards and non-proliferation. Before coming to Texas A&M, she worked at Massachusetts Institute of Technology, and before that, she received her PhD from the University of Cologne in Germany, and has very relevant working experience at the Superconducting Cyclotron Laboratory of Michigan State University and at Yale, though we never met there. So welcome, and thanks for being here.
Thank you for the wonderful introduction, and welcome everyone. Good afternoon. I'm Farheen Naqvi from Texas A&M, and today I'm going to discuss about how neutron resonances can be used to identify certain isotopes in a target. And I'll talk about a mobile and portable setup that we have built at MIT and now building at Texas A&M for identification of fissile material. For those who have noticed that the title of my talk, which was published, was a little open-ended. There was this material missing in the title of the talk. That was done deliberately so that the mystery remains and you guys are more motivated to come here and attend this talk. So the real title of my talk is a mobile NRTA setup for identification of fissile material. The main or the long-term goal of these projects is to identify special nuclear materials, especially the sensitive uranium and plutonium isotopes. And with that, we want to be able to prevent the illegal trafficking of these isotopes or stop any malicious activities because these are sensitive isotopes. Now, our choice of experimental technique is neutron resonance transmission analysis method. There are some conventional methods as well that are available to us. Why did we choose NRTA? I'll discuss that in a minute. But let's first talk a little about the conventional methods, which are passive measurements, passive gamma and neutron measurement. So I'll be focusing mainly on uranium and plutonium isotopes here. So if you look at uranium-235, you see that it doesn't emit that many neutrons. So the choice, usually the general choice of the technique that people use for identifying the presence of uranium-235 is through gamma measurements. Passive measurements means you look at the radiation that is being emitted by the radioactive material. It can be neutrons, it can be gammas, and you try to figure out, you try to count the neutrons, and with that counting, you estimate the mass of the material present, or you look at the gamma rays and try to correlate, look at the energy of the gamma rays and try to see what isotope is emitting those gamma rays. So uranium-235, look at the second last column. The energy of the gamma rays that it emits is around 144 keV and 186 keV. Those are low. Those are considered as low energy gamma rays. So it's very easy to shield them. You put some lead around your material and they're gone. And if you have bulk material, there is some self-absorption as well. So that's the disadvantage of using passive gamma measurements for identifying uranium-235. The good thing is for uranium-238, these energies are considered as high energy, so 766 keV and 1 MeV. You can still detect them with some amount of shielding. And we're lucky here because uranium-235 almost all the time comes with uranium-238. So if you can detect the presence of uranium-238, you can send that sample for further analysis and see how much of uranium-235 is present, if it's enriched, if it's natural uranium, low enriched uranium, highly enriched uranium, and so on. Now, when it comes to plutonium isotopes, it emits a lot of neutrons, so you can count the number of neutrons, which is called as passive neutron detection, and can correlate the mass of plutonium isotope present in your material. Then there are some active neutron techniques as well, where you just shoot a beam of neutrons on your material and look at what gammas are emitted, or how many neutrons are emitted after the interaction of the neutron beam with your material. Now, most of these isotopes, most of these methods are not isotope sensitive, except the gamma measurement. So if you want to know whether this material consists of uranium-235 or uranium-238 or plutonium-240 or plutonium-239, you want to use a method that is sensitive to the isotopes that are present. And that's why we are using the neutron resonance transmission analysis method, because resonances, they are a unique fingerprint of nuclear structure. Now, each of the nuclei, like electrons are arranged in certain energy levels in atoms, protons and neutrons are also arranged in certain energy levels in nuclei. So each of these nuclei, they have a different structure, internal excited state structure, that you can probe to find out which element or which isotope is present in the target. So what we do in neutron resonance transmission analysis is, you have an unknown target, you shoot a beam of neutrons, the energy of neutrons is in epithermal range. So few EV, here on this plot you can see 1 to 10 EV. That's we deal with energies around 1 to 100 EV. We shoot that beam of neutrons on the target and look at the resonances. What can happen in this energy range is two kind of reactions. One is just elastic scattering, and the other one is the neutron can get absorbed. These are the main reactions that can happen in this energy. The neutron can get absorbed. Now, if your energy is equal to the resonance energy, which matches with the energy of one of the levels that is absorbing that neutron, the probability of absorption of the neutron increases quite a lot. So here in this plot on the right side, you can see these peaks. These peaks, this is y-axis is the cross section of neutron absorption. So that probability increases considerably when there is a particular energy, which is the resonance energy. So what we do in NRTA is we shoot a beam of neutrons on the target, and we look at the energy of the neutrons that are transmitted through the target. So based on the energy of the incoming neutrons, resonance will occur. Those neutrons will get absorbed, and the ones that are transmitted through the neutrons, if you look at the energy pattern, this plot over there on top, you'd see dips at those energies where the neutrons got absorbed. So if you look at the energy spectrum of the neutrons that are transmitted, you'll see a pattern of dips, and those the energy of those dips will correspond to the resonance energies. And this is how, for every isotope, this pattern is going to be different. And this is how you identify that, okay, if this is the pattern of my energies, of the energy spectrum of the transmitted neutrons, this isotope is present in the target. Now on the right-hand side is just a chart of the elemental chart, and we've shown there what different isotopes have. So different isotopes have resonances in different energy range, and our setup can only look at resonances in the energy range of 1 to 80 EV. So most of the heavy nuclides here, so for example, the ones that are marked with black triangles, they have resonances in less than 10 EV range. The gray ones are 10 to 100 EV. So most of the black triangles and the gray ones are the elements that we can measure from in this setup. Now, one of the other very attractive thing about NRTA is, So this on the left side is the resonance plot for the important uranium and plutonium isotopes in the energy range of 1 to 50 eV. Now on the right is the same plot for common shielding materials. You see that there are no resonances in that energy range. There are resonances present for these elements, but they are at much higher energy. So when you have your special nuclear material shielded by one of these common shielding material, you will not have any interference. So that's one of the very important properties of NRTA, especially for this application. Now, NRTA is not a very new technique. It's been there for 40 years. People have used it for 40 years, exactly for the same thing, for identifying the isotopes, for archaeology. So what is the new thing that we are bringing to the table? What is the new concept that we are dealing with? So here, again, NRTA right now can be done at large experimental facilities, like at Los Alamos. There you have neutron sources, large neutron sources with long beam lines, because you're measuring the energy of neutrons that you get from the time of flight measurement. So these are long beam lines with a really good resolution, time of flight resolution, really good neutron fluxes. But if for example, you find a suspicious material somewhere on some of the, I'll give you an example on a border, in a border area, for example. Now, what you'll have to do to apply NRTA for identification of the isotopes is you'll have to transport it to one of these facilities, get the beam line, or get the beam time, do the experiment, do the analysis. That will take a couple of months. So that's not feasible. So what we need is an on-site facility, a material identification facility, which can do the identification thing. So that is what we've built at MIT, at the Applied Nuclear Physics Lab there. What we did was we started with a small neutron generator, which is shown here in this picture. It's a commercially available DT neutron generator. So you produce neutrons by the reaction that's shown in the top, neutron fusing with tritron, giving neutrons of energy up to 14 MeV. Now, remember, I was talking about epithermal neutrons. So we have to bring that energy, the MeV energy, down to EV range. That's like 6 orders of magnitude. How do you do that? You moderate the neutrons. So in the second picture, this is the middle tube is our neutron tube, which is surrounded by polyethylene and borated polyethylene. They act as moderators. Moderators, they elastic scattering, and they bring down the energy of your neutrons to, like, it's a cocktail beam. You have all sorts of energies, starting from MeV down to thermal energies. So that's how we get the epithermal beam. That's our setup over there, the third picture. The second, where you see the lead bricks, our detector is inside a box there, which is surrounded by lead and boron carbide. Lead for shielding it from gammas, the room background, and boron carbide for shielding the detector from the thermal neutrons that are off axis and epithermal neutrons that are off axis. We just want on axis neutrons. And that's the generator over there. Then our detector, which is neutron sensitive detector, is a very simple setup. 3 lithium-6 GS20 glass discs just coupled to the PMP. And this is sensitive to, as I said, thermal and epithermal neutrons. Now, this is how the experimental setup looks like. We had a time of flight distance of around, is it mentioned here? No, it was around 1.6 meters or 2 meters. And our target was kept right in front of the box, which this is the housing for our detector, which had lead shielding and the boron carbide shielding. And yeah, that's it. So that's our target. And we put cadmium in front of the target, because cadmium helps in front or at the back of the target. Cadmium helps in absorbing all the thermals. And we don't want thermal in our spectrum. We just want neutrons of energy around 1 to 100 EV. So these are the results. It's a pretty simple setup. And we spent some time in optimizing it, in optimizing the background, gamma background, shielding, what kind of shielding we want, how to get rid of thermals, how to get rid of off-axis epithermal. But after that, it was like really, I mean, the beam was there, we got the results. So this is the transmitted neutron energy spectrum. X-axis is time of flight. The blue curve is just the theoretical cross sections. So you can see that where you see a peak in the cross sections, you see a dip in the experimental data. That is where the neutrons are getting absorbed. So the first plot over there is for indium target. Then we had tungsten, silver, and depleted uranium. So depleted uranium is mostly uranium-238 there. And I mean, you can see that just by looking at this spectrum, and we could actually fit the experimental data with some very simple model that we built. And we could identify all these isotopes there, even though our resolution is not as good as the resolution that you would get at facilities like Los Alamos. But I mean, it's good enough for identifying, which was the main aim, to show that yes, you can use such a small setup to identify the presence of these isotopes. Now, very recently, we went to PNNL. So as these measurements were done at MIT, it's very difficult to get hold of plutonium isotopes or HEU, highly enriched uranium, in universities. I don't know how it is here, but it was really difficult to work with these materials, sensitive materials at MIT. So we couldn't do those measurements there. We collaborated with National Lab, PNNL, which it's easier to get a hold of plutonium or uranium isotopes there. So this is a target, which is depleted uranium, reactor-grade plutonium, tantalum, and steel. That is how the target was made there. We didn't make it, we just got that target. The main aim was to see if we can identify plutonium or not. And this very first peak, or the very first dip that you see, very first, because this is the low energy side. This is the 1 eV side. Again, x-axis is time of flight. More time of flight means it's slower, which means the energy is less. So this side is 1 eV. It starts at 1 eV and then it goes like this. So this very first, or the very last dip here, is the plutonium-240, and then some of these over here. So black is our experimental data, blue is again the theoretical cross sections. Some of the dips here are for plutonium-239. Now, plutonium-239 is the most important isotope. It has a very low energy dip, which is 0.3 eV. Our setup cannot see that. It starts at, our sensitivity starts at 1 eV, but 240 has that resonance, so you can see 240. And there are all other dips are coming from uranium-238 and tantalum. So this is an actual application of this whole setup on reactor-grade plutonium. So this is, we have not published this data yet, but it will be published soon. So this was about this one project. And the conclusion of this one project is that yes, compact NRTA setup for identification of special nuclear material is possible. We could, so these facilities are, of course, very expensive. Our setup is just 100K. So if it depends on, of course, what application you're using it for, but if you want to identify the special nuclear material, you want to quantify it, you can use this setup for doing that. It's highly portable, it's mobile. Now, The next setup that I'm going to talk about is doing the same stuff, NRTA, using isotopic neutron source. So forget about neutron generator. The sources that we have in our labs, AMB, plutonium, beryllium, can we use that instead of the neutron generator to do similar stuff? So that was another idea that we are working on at TAMU. And here the idea is, again, same thing, measure time of flight between, there we were measuring time of flight between neutron generator and the neutron sensitive detector. Here we are measuring time of flight between a liquid scintillator and the neutron sensitive detector. Why liquid scintillator? Well, neutron generator in the previous setup gives you a time tagged, it gives you a neutron pulse. So you have the start of the time of flight from the neutron generator. Here, the source is a continuous emitter of neutron. How do you get the time zero for your time of flight? So for that, we are using a liquid scintillator that gives us time zero. And it also acts as a moderator because it has hydrogen in it. So this source over here, we started with AMB source. Again, this source emits neutrons up to 11 MeV. We have to bring it down to EV. We need a moderator. So we use liquid scintillator for moderation and to give us a time reference, T0 for the time of flight. So this is the whole setup. And this setup here, the time of flight is just 50 centimeters. So it's like this big, you can put it on a table. You need more shielding for this kind of setup, but it's even more mobile and compact compared to the previous setup. And these sources are present in every lab, so you can build something like that in labs. Okay, so I forgot to mention one thing here. If you want to get time of flight between two detectors, you have to measure coincidences between these two detectors. So your neutron in liquid scintillator should be correlated to the neutron in your lithium glass GS20 detector. So you, in other words, you're measuring coincidences between these two detectors. Now, most of your isotopic sources, they emit gammas as well, right? So what are the different kind of coincidences you would get in these two detectors? Neutron, neutron, gamma neutron, neutron gamma, and gamma gamma. So there are like 4 different kinds of coincidences that you get in this setup. Now, out of those 4, you're just interested in the top one, neutron, neutron. All others are background contributions. How do we get rid of these? The first way of getting this rid of this is the very first set of data. So this can be better. This is a liquid scintillator PSD. You can separate between fast neutrons and gammas using liquid scintillator. It can be a better plot, but this is just first set of data. So using liquid, why we are using liquid scintillator, there's a reason, and that is that it can differentiate between fast neutrons and gammas. So just by this first band is fast neutrons and the second band is for gamma. So just by selecting the topmost band, you get fast neutron. So what does it do? It just gets rid of gamma and gamma gamma coincidences. So out of 3, we got rid of 2 contributions. How do we get rid of neutron gamma coincidence? Now this is the light collected or energy deposited in your GS20 glass. This detector is not as efficient as the liquid scintillator in separating neutrons from gammas. So this little bump that you see is for epithermal or thermal neutrons. If you select that, that will give you neutron-neutron coincidences. But this red curve here is the room gamma background that we saw in our detector. It cannot differentiate well between neutrons and gammas. So that bump that we are selecting has a huge gamma component underneath it. So this third neutron gamma coincidences we couldn't get rid of with this setup or the detector thicknesses that we were working with. So the result of that is, this is again the first experimental result for this setup. Time of flight counts. You remember those plots in the previous setup with really deep dips. For silver, that's our dip over there, around 17 microseconds. It's at the right energy. It's really shallow because there is a huge gamma background in this data, but it's there. So we have to work a little more on this, get rid of the background, and hopefully we'll see better and more pronounced dips in this data. So this was for silver target. Again, we are dealing with sources. The neutron flux or the number of neutrons that we get from the sources, 10 to the 4 neutrons per second. Neutron generator is 10 to the 6 neutrons per second. So that data was 3 hours. This data is 40 hours of data. That's our limitation here. Now this is for tungsten target. The vertical lines that you see are the energies where the dips should be. There is some neutron deficit there. I wouldn't say that you can use this data to identify the presence of tungsten because the dips are not easily identifiable here. But again, there's a lot of background there, so we are working on that. The expected impact of this work is, again, the same thing. We're talking about a setup which is much, much cheaper, more portable, less shielding. It's smaller and it requires fewer regulatory steps. But there are constraints, there are limitations of this setup, and that is it took us at least 2 days to collect that data. I mean, it will get better if we can get rid of the background, if we can use higher, that will allow us to use higher activity source. If we can do that, then the collection time would get reduced. But for now, it's 40 hours or so. And yeah, so that would be the expected impact. You can actually have this setup. It's pretty simple in most of the labs, very cheap, very easy to work with. So with that, the next steps for this particular setup is how do we plan to get rid of the background? Right now, we are working with, so this data was taken with 1 centimeter thick GS20 glass, which is quite thick. So we ordered something which was 5 millimeters, so half the thickness. And we're expecting that if it will be thinner, the neutron gamma separation would be better. So we have those detectors now. We'll start setting up the whole thing and start taking data. Then there are other ideas of reducing neutron random correlations. We can use active veto techniques and active coincidences techniques. Those are a little more in depth. If you have any questions about that, how we want to do it, we can discuss. And yeah, one important changes that we would like to make to this setup is use a californium source instead of an AMBI source. That is because AMBI has neutron energies up to 11 MeV. So you require a thicker moderator to bring those 11 MeVs down to E. If you start with a source that has less energy, that emits lower energy neutrons, you don't need such a thick moderator. That affects your resolution as well, time of flight resolution or energy resolution. So we'll start with californium and see how that changes our spectrum, the time of flight spectrum, resolution and stuff like that. The conclusion of this work is that NRTA measurements, again, with simpler setup and isotopic neutron sources are possible. Is possible. We are limited in neutron flux, time of flight, resolution, but it's really cheap. It's easy to put together, easy to work with, fewer regulations. So with this, yeah, I would like to thank you all and thank the the agencies that funded this work. Thank you.
I'm just wondering, like, if you can detect, let's say, like, honest or like, the data by the specific, like, maybe like not like, pure, certified, or like a 2% in rate, during sample you like that, or
We can, at PNNL especially, we had uranium-235, highly enriched uranium-235 sample different enrichment. So we did measurements with that sample, and we're analyzing that data. And it looks like, that yes, we can find out the enrichment. So we can quantify how much of uranium-235 is present, and that will translate to getting the enrichment levels up. We can do that.
do you have any issues with, materials with that, both the space, but issues with.
Yes, so the resolution is, I'll go to the other. Not this. This is also not a good example, but so we have done measurements with, let's say, tungsten and silver together. Tungsten and silver, if you look at the biggest dip there, they're very close in energy. We were able to, it depends on what's the resolution at that energy, but we could resolve these two. But there are cases, especially tungsten and uranium-235, when they're together, you cannot identify one or two. If there are overlapping, you cannot identify those. But most of the isotopes, they have more than one presence. So if one is not, you cannot resolve one, you can most probably resolve the other two and can figure out if that isotope is present.
For example, I want to detect uranium-235 neutrons, according to resonance energy, and it is surrounded by so many other isotopes. The neutron gets scattered, and it's not absorbed then because the resonance energy changed. In that case, we are not being able to detect that uranium. And it can happen the opposite also, like there is no uranium, but we are sending energy, neutrons with same energy, it gets scattered and ultimately gets absorbed by some other isotope. And we are detecting uranium, although it is not there. So these two might be some false detection. How to avoid it?
So this is a particular example of what you're saying. We have a mixture of isotopes here, or several targets there. It's not a pure target, right? And some of the targets that will not have resonances in this energy, they will still have some kind of absorption happening, some kind of attenuation just because of scattering that we're saying. But if there is a strong resonance present, you will still see it, as long as you do not, as long as neutrons are reaching your target and are able to come out of it, you will, and if it's a strong resonance, you will still see some signature there. It will be, so there is a continuous line, for example. Here, there's this continuous line, and then there is a dip. If you have two targets present there, one of them doesn't have any resonance, it just attenuates the neutrons just by scattering, and the other one has a dip there. So what will happen is your dip, your constant or the continuous part will come down because of the attenuation, and your dip will appear as if it's shallow. But it will still be there, and it all depends on how much of this attenuation is. If it's really huge, then at some point your dip will disappear. So that happens, that happens.
Current two-thirds of the radiation is very low. It's mostly other beyond 230. In that case, the emission of those scattering will dominate, right?
Well, it depends. If you have an HEU, then uranium-235 is.
That's why I'm going.
So here, this last plot is depleted uranium. That's like how much? I think 99 point something percent uranium-238, and then 25. Then uranium. Rest of it is uranium-235. Very, very small amount. You cannot see uranium-235 there. It's just uranium-238. But uranium-235 is present. It all depends on how much of that material is present. And we are doing the sensitivity study that what's the limit where we will not see it.
Yes, I have a question regarding your setup. At the second setup, you use a DC generator to generate the action unit of the.
First, the second setup,
Yeah, you use the DC generator to generate a neutron beam, right?
that was for the first setup.
Of the first.
Yeah.
Okay, and if I understand correctly, you first use plastic to solar neutron, and then you use a collimator to collimate the beam, right? And my question is, what is the software after solarization and collimation?
I don't know. So your generator emits 14 MeV neutrons, right? We are not interested in those neutrons or KeV neutrons. We are interested in EV neutrons. So the how 1 in million is the number of neutrons that are reaching our detector, number of epithermal neutrons that are reaching our detector. That's the efficiency. That's the efficiency of the whole moderator and polymer, 1 in million.
So the neutron generator source is very on 10^8. So after collimation is scared with 300 neutrons per second.
10 to the 8 is what, 4 pi?
Yeah.
Right, so I don't know, we have not quantified that. As I said, I don't know for the fast neutrons because we are not interested. They're not interfering with our signal, so we never quantified that or that flux. We are not interested in fast neutrons, but you've worked with DT neutrons, so you know about this more than me.
Yeah, because I'm also interested in the
Okay. Yeah, epithermal neutron, as I said, the efficiency is really low for epithermal.
So anyhow, you're able to do fast, is that 3 hours, right?
Yes, 3 hours for this data, but within 15 minutes, we can start, And with the new DP generator, so we've got a new one, it's even faster than that because the flux is higher.
So as far as application purposes, could you imagine this being a sufficient tool on its own? Or would you imagine this needs to be a part of like a larger tool set? If we're being applied as you maybe like a border or something.
It depends what you want to do. So if you find, well, again, there are so many factors determining what kind of technique you want to use to get the information that you want to get. Now, if you find a suspicious material, which is, it looks like that it's shielded by lead because it's heavy. So, maybe lead is involved. So you wouldn't, if it's really thick, you wouldn't use this method because the neutrons wouldn't be able to reach your target because you have thick, it's shielded by thick lead. So for that, you will probably use X-ray imaging or something. X-ray imaging is also not possible with that much amount of lead. So some imaging techniques so that you could find out what's the Z and then try to dismantle it and then take out the target and then use. So it all depends on what you have, what the situation is. If you just see some material which is not shielded, you can put it in this that up and figure it out.
Okay, any final questions? So I have one, did you test in your setup in your lab, did you test triple coincidences?
Triple coincidences for,
You have some real states that are fitted with the gammas. And so you can toggle the gamma and then that gamma corresponds to a neutron. Of course, it is very low probability, but you get rid of the background.
we haven't tried
Yeah,
that,
that's
but-
but I think. it's-
but there was, so there's another PhD student who's working on the gamma part, the gamma neutron coincidences part. I don't know what's the status now because of.
Yeah. But you toggle the gamma and then let the neutron thermalize and toggle the neutron, and then you have a third stage. So you are
But
really.
that will reduce our statistics quite a lot.
Very much, you will, but you also got.
Yeah. Then you can get rid of a lot of background, especially for the second one, but I don't know, the second one already has such a low statistic.
Yeah, we will, see, I've done this, but we did the practice spectroscopy calculation, and you can, yeah, this back.
Okay.
Yeah, but it's
Thanks
right.
for keeping the lead.
Great, so let's stand up.
Yeah, I did. Yes.
Thank you.
Thank you. Thanks.
Well, very nice to meet you. Over.
I was like farming as well.
Yeah, I was supposed to, but then I got. Then my husband. Yeah. No, there's one. Yeah. Right. Yeah. Thank you. Then I asked God, we want to judge it. We can put one in this guidance, in fact, the fix with the move is not going to find out. So hopefully we can get it good. I don't know if we want to, it depends, yeah, because now the news source is coming, where are we going to put it? Okay, let's have a conversation. Thanks. Thanks. This or the SNN, and then you throw the human material and other results. What about something in the finish? And there other material that is possibly looks very much like the SNN.
If you shoot your material, that's.
How much, either few or how much? If there's something there, you would say, well, there's something.
Yeah.
Could be tungsten.
Well, as you said, the tungsten has negatives, but then other, if one of them is shielded by tungsten, if, and there will be others that we can use to identify. Maybe we won't be able to do the quantification for identification. But we are doing that. They are doing that.
I mean, yeah. Oh.
So in senior design process.
Mhm.
So, what is that you have at this one?
Yeah, drones.
Yeah, we have a drone in there.
How big of a tank did you use? Because, I mean, because it's all, yeah, so, you have to make it work,
Yeah.
okay? No, so, it has not been used in several, okay? So you have to see it, check it, yeah, to calibrate it and all that.
It's,
But you need to put it on the drone.
yeah, so the room can carry. I need to. It can carry some. The room space.
Okay, maybe come, let's talk tomorrow. Come and see me and we can walk around. And see if that's the right thing to do. Okay. Okay, to. Oh.
Yeah, yeah.
Yeah, okay. Maybe it's point, maybe you can go and walk to the hotel. And then I'll come to you.